The universe exists because of you is not merely a metaphorical statement, but rather a reflection of a fundamental shift in how modern physics understands the relationship between observer and reality. In the classical Newtonian paradigm, the universe was viewed as a giant, self-contained machine operating according to definite laws, without requiring human involvement. Reality was objective, fixed, and measurable without affecting it. However, quantum mechanics shakes this foundation. It shows that at the microscopic scale, the existence of something cannot be separated from the process of observation itself. Quantum experiments show that particles such as electrons or photons have no definite properties, position, momentum, or even definitive existence until they are measured. Before observation, the system is in a state of superposition, an overlap of multiple possibilities. When a measurement is made, the superposition collapses into a single specific outcome. This phenomenon is called the measurement problem, and to date, there is no single answer as to why or how this process occurs. The involvement of the observer is at the center of controversy. In the Copenhagen interpretation, Bohr and Heisenberg, physical reality is meaningless without the act of observation. The wave function represents only potential, not actual reality. But when a measurement result emerges, that potential seems to become real through interaction with the observer or measuring instrument. This raises a profound question. Is reality independent, or does it emerge only when observed? It is important to emphasize that quantum mechanics does not explicitly state that human consciousness creates the physical world. Rather, it highlights the limitations of the classical view that separates the subject, observer, from the object, observed. Thus, the idea that the universe exists because of you should be understood not as a mystical dogma, but rather a scientific reflection of the fact that the act of observing plays an active role in determining how reality manifests to us. This understanding opens the door to a new paradigm, that reality may not be a passive entity waiting to be discovered, but rather a dynamic process shaped by the interactions between observers, systems, and information. This begins the scientific quest for the quantum laws of existence, where consciousness and physics begin to intersect in an effort to understand the nature of existence itself. To understand why quantum mechanics challenges the concept of objective reality, we need to look at its mathematical foundations. In classical physics, the state of an object is described by its position and momentum, two quantities that can be measured with infinite precision. However, in the quantum world, this description is replaced by the wave function, a mathematical entity that contains all the probabilistic information about the system. The wave function does not give a definitive answer about where a particle is, but it does provide the probability that it will be found at a particular location when measured. The Schrödinger equation describes how psi evolves deterministically over time. In the absence of measurement, the state of the system would continuously change in a smooth superposition of many possibilities. But when a measurement is made, it is as if all these possibilities collapse into a single definite outcome. This is the great mystery of the so-called measurement problem. Why does the process of measurement produce a single reality from a sea of possibilities? In a formal framework, the theory does not specify the physical mechanism of this collapse. It only provides the final outcome, the probability of the measurement outcome. This phenomenon challenges the concept of classical realism, that the world has certain properties even when unobserved. In the two-slit experiment, for example, a single particle can produce a characteristic wave interference pattern if its path is not measured. But this pattern disappears when we try to determine which slit the particle passed through. This means that simply attempting to obtain information fundamentally changes the experimental results. This fact reveals that information and observation are not mere adjuncts to the experiment, but rather an inherent part of quantum reality itself. Some physicists attempt to interpret this anomaly through the theory of decoherence, the process by which a quantum system interacts with its environment, causing an apparent collapse of superpositions without the need for conscious awareness. Although decoherence mathematically explains the transition from quantum to classical, it does not eliminate the most fundamental question. Is the collapse merely a statistical illusion, or is there an existential mechanism linking observation to existence? The measurement problem, then, is not merely a technical one, but a window into the nature of reality itself. It forces science to re-examine the boundaries between subject and object, between knowledge and existence. While in classical physics, the observer is merely a passive witness, in the quantum world, the observer becomes an integral part of the narrative of the universe, and perhaps one of the determining factors in why the reality we experience appears as it does.
After exploring the theoretical and interpretive foundations of quantum mechanics, we arrive at a tentative conclusion. The universe no longer seems fully explainable as an objective entity existing independently of the observer. From the two-slit experiment to Wheeler's participatory theory, all suggest that the act of knowing plays a role in determining how reality manifests. However, to claim that human consciousness creates the universe is a leap beyond the empirical boundaries of science. Such a claim is metaphysical, not scientific, because it cannot be tested through controlled observation or experimental replication. In a strictly scientific framework, quantum reality is more accurately understood as an information system formed through interactions. The wave function does not describe the physical world directly, but rather represents the potentialities available to the observer. When a measurement is made, that information is updated, and the reality we perceive is the result of a consistency between the observer, the system, and the environment. The mechanism of decoherence, for example, explains how interactions with the environment effectively cause superpositions to collapse, making the world appear classical to human consciousness. Thus, nature does not need to be conscious to exist, but its existence only becomes meaningful to us when measured.
The mystery of the relationship between observer and reality in quantum physics has given rise to various philosophical and theoretical interpretations that attempt to explain how the universe determines the results of observations. Because the Schrödinger equation only describes the smooth evolution of the wave function without explaining how a concrete outcome arises, scientists have proposed various interpretations of the true meaning of the collapse and the role of the observer in it. The most classic interpretation is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. In this view, the wave function is not a description of objective reality, but rather a conceptual tool that helps us calculate the probabilities of measurement outcomes. Reality, according to Bohr, is only defined when an observation is made. Before a measurement, all possibilities are potential and only become actual when they are measured. This view places the observer as a crucial element, not because their consciousness creates reality, but because the act of measurement determines how the world appears to us. However, not all scientists are satisfied with this position. John Archibald Wheeler expanded on this idea with the concept of the participatory universe. According to Wheeler, the universe is not a finished entity, but rather a process that is continuously created through the participation of the observer. In this framework, the act of measurement by a conscious being plays a role in manifesting the reality of quantum potential. He calls this law without laws. The laws of physics emerge as stable patterns of repeated interaction between consciousness and the world. In other words, we are not mere spectators, but part of the cosmic creation machine itself. Another interesting interpretation is cubism, quantum Bayesianism, developed by Christopher Fuchs and his colleagues. Cubism views the wave function not as a property of a physical system, but as an expression of an observer's subjective beliefs about possible outcomes. In this view, quantum mechanics is a theory of the beliefs of agents interacting with the world, not an objective description of the world itself. Each observer has their own probabilistic reality that is updated each time they interact with the system. Meanwhile, relational quantum mechanics, RQM, proposed by Carlo Rovelli, proposes that physical properties are not absolute, but relational, depending on who is observing. In this framework, there is no universal description of the state of a system. Each measurement is meaningful only relative to other systems. For example, the position of an electron might be defined for observer A, but not necessarily for observer B until they interact. Reality, then, is not a singular objective entity, but a web of interdependent relationships. All of these interpretations, though differing in direction, share a core commonality. They blur the boundaries between observer and nature. Reality is no longer seen as something out there, but as the result of the interweaving of information, interactions, and experiences. With the emergence of this paradigm, the concept of existence shifts from a passive entity to a dynamic process, a symphony between consciousness, matter, and the probabilistic laws of nature. However, it's important to remember that there is no empirical evidence to confirm either interpretation as correct. All remain conceptual, serving as a philosophical bridge to understanding how the quantum world creates the reality we experience. But if there's one message emerging from all of them, it's this: reality doesn't exist without your participation. Quantum phenomena have not only shaken theory, but also shaken the very foundations of how we understand the relationship between observer and reality. Experiments designed since the early 20th century have shown that the line between what is observed and who observes is far more blurred than classical science ever imagined. One of the most influential experiments in this regard is the double-slit experiment, a simple yet logic-shattering experiment. When a beam of electrons or photons is fired through two narrow slits and no path measuring device is present, the particles produce a characteristic wave-like interference pattern on a detection screen. However, if a device is placed to track through which slit the particles pass, the interference pattern disappears and is replaced by two lines, resembling the behavior of ordinary particles. This fact suggests that the decision to observe a particle's path determines how reality will behave. In other words, the act of observation not only reveals reality, but also helps shape it. This concept was taken further by John Archibald Wheeler in an advanced version called the delayed choice experiment. Here, the decision to measure the path or not is made after the particle has passed through the slit, even when the particle should have already chosen its path. Surprisingly, the results still show that observational choices made after the fact still influence whether the interference pattern appears. It is as if the particle waits for the observer's decision to be made, only then to determine its past behavior. More sophisticated experiments such as the quantum eraser, Scully and Druhl, 1982, Kim et al., 1999, reinforce this paradox. In these experiments, the particle's path information can be erased or retained after the event has occurred. The results show that only the presence of information, not any direct physical action, determines whether a wave or particle phenomenon emerges. When the path information is erased, the interference pattern reappears. When the information is retained, the interference disappears. The universe seems to care about what the observer knows, not just what they do. The implications of these experiments are profound. They challenge the concept of reality as independent of consciousness, revealing that knowledge and existence are intertwined in the quantum fabric. However, it is important to emphasize, there is no evidence that human consciousness directly alters matter. Rather, it is that physical systems and measurement information form an inseparable whole. The universe, it seems, can no longer be understood as a passive stage on which events unfold, but rather as an interactive network in which every act of observation becomes part of the fabric of reality itself.